Chris Farrow. I'm going to be talking to you on this webinar about resilient, traceable, and trusted time for data centers. So quickly, before we start, a very brief interview on Chronos, the company. The best way to describe us is we are subject matter experts on time and frequency systems, timing and synchronization. We've been commissioning, installing, supporting these systems for over 30 years, 35 years as of this year. We're involved in some of the standards groups. We're active in many of the markets that use time and frequency. And we have some of our own products. We develop some handheld interference detection and other interference detection solutions and pieces of test equipment. Our installation team have installed timing receivers, GNSS-based timing receivers and timing systems all over the world. So for a small company, we have a global reach, global footprint. So that's Chronos. The subject of this webinar, this talk today, is about how time and time as a service can improve functions and processes within data centers. But time really is, it's often referred to as an invisible utility. It's something that supports many industries, processes, and for legal requirements, lots of things have to be legally traceable to trusted sources of time. So started really with transportation industries, telecommunications, right up to 5G. The latest telecommunication systems have very tight time synchronization requirements to squeeze the last bit of efficiency from the radio spectrum that they're using. Financial industries, financial services use timestamps, and again, a legal driver there, a legal regulation that these timestamps are traceable back to a legally verifiable source. The power industry for generation and management of power grids and power distribution uses time and time synchronization. The broadcast industry, and really most of the latest technologies, the leading edge of technology, things like AI and machine learning, the Internet of Things, cloud services, lots of these industries use either large disparate networks of sensors like Internet of Things, where timestamps are important. So it's across the whole board. Time and accurate timestamps are really driving most of this sort of modern hyper-connected world that we live in. And for all of these systems, really, the source of time is ultimately atomic clocks that are traceable to UTC that are often delivered via satellites. So the most common form of timing receiver is a GNSS or a GPS satellite time receiver that provides the underlying time for these systems. So specifically focusing on data centers today. What is a data center? Well, there's this stereotypical view, the image that's on screen now, in sort of Hollywood films and TV. It's all very smart and very well lit, looking very slick. Stereotypically, the internet or the cloud is always referred to in that way. Obviously, in the real world, data centers look slightly different, but fundamentally, a data center is a physical location, somewhere where power, space, and cooling is offered. In terms of co-location, data centers, the data center provider, the owner of the building and the infrastructure, is a different entity to the operators, the network, the equipment that's put into those data centers to provide interconnectivity. They are a little bit like internet exchange or a telephone exchange. Network service operators can put equipment in, sometimes in cages, sometimes behind cages like these things here, very, very secure. Or cloud services like Amazon, Google, Microsoft, all these big providers of cloud services have what's sometimes referred to as hyperscale data centers, where they own not only the physical infrastructure, but all the servers in the data centers as well. So typically the offering is power, space, and some sort of cooling facility. Now, what about time? We've already seen that time underpins lots of modern processes. and business procedures and technologies. What about adding time as a service to the data center? So why do we need accurate time? Well, sometimes there are technical reasons. Distributed database access is a good example. Google Spanner is a well-known distributed database that's used globally. So we need to coordinate writing and reading from that database to make sure we're writing and reading data in the right order all around the world. Distributed sensor networks in the power industry, measuring voltage and current on power distribution systems is a key way of looking for faults and monitoring when something has gone wrong in that in that power transmission industry. And often radio systems schedule, transmit and receive, and 4G, some of the LTE advanced technologies in 4G and 5G, some of those services are really good examples of radio systems that need to schedule, transmit and receive. And again, going back to a comment I made earlier about utilizing the radio spectrum as efficiently as possible to get the most bandwidth. We all hear of 4G and 5G services delivering hundreds of megabits, maybe gigabits per second to a single handset. So to enable that, the radio resource has to be very efficiently managed in terms of bits per hertz of spectrum that can be used. And often that includes very tight time alignment on scheduling, transmit and receive. And often, as I've alluded to earlier, there are regulatory reasons. For example, in the European Union, this MiFID II directive puts very strict requirements on financial institutions that are doing, for example, high frequency trading, that all those reportable events, as they're called, need to be timestamped to within 100 microseconds of UTC and a legally verifiable and traceable source of UTC. This slide really is just a very simple graphic that illustrates this globally distributed database example where we have physically separate data centers all forming part of the same database, writes and reads happening at different times, and obviously we need to make sure that the writes are always perceived as happening in the correct order wherever you are in the world. So for that example, time systems and time synchronization systems are built into the way some of these databases function, but there's a very good requirement, very strict requirement on why time is important for those sort of services. When we're talking about time, what time is the right time? So UTC is an acronym, Universal Coordinated Time. It's a compromise between the French and the English versions of that phrase. It's a global time base that's made up of frequency of atomic clocks in all the primary labs around the world. It's usually delivered to an end user by a local GPS receiver. That's not the only way of doing it, but it's certainly the most common way of doing it. So GPS is an American system, a global positioning system. There are other constellations. So GNSS is a generic acronym, Global Navigation Satellite System, GNSS, that describes all of the satellite navigation systems. So GPS is from America. There is a Russian system, GLONASS. The European Union have created their own system known as Galileo, and there is a Chinese system known as Beidou. So all of these systems, although they are fundamentally navigation systems, they work by being synchronized and sending synchronized messages and having a time base that's traceable back to a UTC source. So typically these GNSS receivers are the easiest way of getting UTC traceable time into things like primary reference clocks for PTP and NTP. So PTP is the precision time protocol, NTP is the network time protocol. Both packet-based messaging protocols of transferring time over packet networks, so over the sort of network infrastructure that connects various servers together within data centers. So you'll typically see primary clocks using GNSS receivers as a reference to UTC and using NTP or PTP to then move time around the data center. So these time servers act as distribution points where they receive UTC and then distribute that out to whatever applications are running in the data center that need to use accurate time. So in terms of security, physical access controls are very extensive. I've been in a few data centers, both in the UK and a couple within Europe. And typically you need to show government ID. Some of them have fingerprint scanners to let you in the room. Some of the co-location data centers, where space is sold to individual operators, the operators' cages themselves are sometimes protected by things like fingerprint scanners, some sort of biometric scanners. So the physical access controls are very extensive. Typically, some of them, they're not only connecting into sort of public networks like the internet, but they're sometimes more often private networks or isolated networks. But in terms of the time receivers that I was just talking about, the GNSS receivers, this is a photograph from one actual data center installation that we visited. We tend to see sort of ad hoc installation of these GNSS antennas by whosever equipment in the data center needs a time reference. So you see some of them are actually provided with lightning protection. You can see this box here has got an earth lead from it. So this protects if there's a lightning strike. Obviously these antennas are sometimes the highest thing on the building, so it's very easy to conduct a lightning strike or conduct all the energy into the equipment room. So some of these are fitted with lightning protection boxes, some of them aren't. Depending on the end user and depending on the application, typically you might see sort of enterprise users use their traditional installers who are not maybe familiar with some of the problems with these type of antennas. So some of these antennas are installed without lightning protection. So if there is a lightning strike, you're going to get a lot, megawatts of energy delivered right into some of these cages, which is going to cause havoc. And these antennas probably mounted too close together. There is a recommended minimum spacing. So, there are all sorts of physical issues with installing these antennas, but also in terms of security, the physical access controls are extensive, but with a jammer or a spoofer, if you wanted to interfere with the time signal and cause problems in the data center, you could drive or walk past with a jammer or a spoofer, and these radio signals are all, these antennas are all easily accessible from outside of the data center. So on one side, physical access is extreme, but the radio access is lacking at the moment in terms of security. When these satellite navigation systems were first designed, going back GPS in the 1970s, when it was first fully declared live in the 1990s, probably even then it wasn't thought that they were originally designed as military systems. It wasn't thought that civilians would have the capability to be able to spoof or even maybe jam the GPS signals. So any local receiver must have some sort of protection against jamming and spoofing, otherwise all the services in the data center become vulnerable to jamming and spoofing. And obviously, if there is some sort of interference, then you need your time system in the data center needs to be able to hold over to maintain accurate time for some period of time until that problem goes away. But there's an explosion of privacy jammers. Now everybody's aware of sort of vehicle tracking, fleet and business vehicles being tracked, their location being logged. You can buy these sort of so-called privacy jammers on the internet. This plugs into a cigarette lighter auxiliary power socket in a vehicle and just creates a noise signal that is much more powerful than the signal from the satellite. So all these satellites are in orbit around roughly 20,000 kilometers away. So by the time the signal gets to the surface of the Earth, it's very, very low power. They're all around the same band. They're all around 1.5 gigahertz. So it's relatively trivial to build a noise source, a radio jammer that will knock out a GPS signal. So obviously, if this is driving past a data center, we could have a problem with all the timing receivers being unable to receive their time source. But also, sort of worse than that is spoofing is now possible. You can go on the internet, again, use Google, tutorials on YouTube telling you how to use a Raspberry Pi, a software-defined radio, which you can buy for a few $100s. You can download code from GitHub and you can compile and run and create something that will generate fake GPS signals. So the problem with this, the reason why this is an issue, is we can spoof time. So not only can you spoof your position with one of these systems, but you could drive or walk past outside a data center, have all those antennas on the roof, and spoof time and cause havoc with all those services that we know are running within the data center to use time. So in terms of improving time as a service, being able to offer secure, resilient, and traceable time for data centers, there are three areas that we need to look at: the security of the time signal and the traceability being two of them. So security, we need a system that can work out if the radio signal is fake, if it's being spoofed. If it's being spoofed. We need to be able to ride through periods of jamming, and we also need a signal that's traceable and resilient. We need some sort of resiliency in terms of local outages and hardware failures and things like that. And the time distribution plays a part of that, whether it's PTP or NTP. So to address the security concerns, there's a relatively new product category that a few manufacturers have put products out into the market. And this concept is a GNSS firewall. So this is a system that has a GNSS antenna. It looks at the signal from the sky and it performs validation on that signal. So it looks at whether the signal power levels are correct, whether the position is moving around more than you would expect. Obviously, this sort of infrastructure with timing receivers are stationary antennas, so they're not expected to move at all. The spoofer that I showed earlier on the previous slide that was based on a Raspberry Pi, similar systems to that often use default data in some of the messages. So some of the messages that the satellites send to timing receivers, in the real live sky signal, they have operational data in, but in the spoof signal, some of them have default settings. So again, this sort of idea that a GNSS firewall can look at the data in the actual messages rather than just extracting the time signal and putting faith in it. And this is what these firewalls do. This particular model from Microchip has two outputs. It has a validated output, which is really the sky signal. So it's the antenna output, which it passes through until such time as it detects that there's a problem. If it thinks the signal is being spoofed, it will turn this signal off. So the validated output is either good sky signal or it's not there at all. And that's obviously aimed at pieces of equipment that have built-in holdover. So if you have a time server that already has a rubidium atomic oscillator in it, then this is probably the configuration that you want. All of the timing receivers that don't have anything like rubidium, you probably want to use this other output on here, which is, it's called a hardened output. Now this again, this is a simulated output. So it's doing the same thing really as the Raspberry Pi is, but much more, with a lot more functionality built in there. So it's looking at the sky signal, it's getting the time from the sky signal, and it's using that time base as a reference for this simulated GPS signal. The good thing about this is that this could, all those antennas that I showed on the picture before, all those systems could then be supplied from this one hardened output. So we could protect everything within the data center with just this one piece of equipment. So again, we can add backup time signals to this. So we can pair this product with a cesium atomic clock, in which case if the sky signal was either jammed or if it was spoofed for a long period of time, we could fall back to using our cesium atomic clock as a frequency reference, and we could provide a GPS signal to all the legacy timing receivers that are in the data center. Excuse me, sorry. So that's the GNSS firewall, a relatively new concept. We can deploy it in different ways. As I've mentioned already, the validated output, particularly for primary reference time servers that already have some sort of holdover built in. The hardened output can be used to supply legacy timing equipment that has that's looking for a GPS signal. We can supply it from this unit, and then you can let this unit decide if we think the sky signal is being interfered with. The third mode of operation is really just for monitoring only. So this unit comes with a built-in web interface, a web GUI that you can control it and configure it with. Excuse me. Or it integrates with the time picture management system. So you can use this as just an interference detection system. So if you have data centers around a geographic area and you want to look at whether there are any incidents, you could use this particular third mode. So in terms of security, we've addressed the GNSS firewall. In terms of reliability, that's really resiliency or redundancy. We start to introduce this concept of building network architectures that support multi-node virtual PRTC. So PRTC is a primary reference time clock. It's an acronym that came from the telecom world, but it's moving over into other market segments. It really means, I'll illustrate later on the next slide exactly what the network architecture looks like, but it means you can have the primary reference time clock performance, so you can have within nanoseconds, within tens or hundreds of nanoseconds of error to UTC at remote nodes that are only connected via network connections that don't necessarily need to have that vulnerable GNSS receiver connected to them. And obviously these time servers, the time provider 4100 and the S600 or S650 support both PTP and NTP. And something that's often overlooked is the importance of being able to support multiple PTP profiles. So we could support telecom PTP profiles to get timing signals over network connections, and support other PTP profiles, like maybe the enterprise profile, to support the servers that are within the data center. But I want to talk a little bit more about this virtual primary reference time clock, the virtual PRTC. Now this is enabled by a mode of operation of the time provider 4100 known as the high performance boundary clock. So these nodes here, you'll notice, are designated as HPBC. So this is a high performance boundary clock. So it's a PTP boundary clock. And these are connected via a DWDM network. And in this particular configuration, to achieve these accuracies, you need a dedicated wavelength, a dedicated lambda between these two. These units support SFPs, bidirectional DWDM SFPs. So you're effectively, even though PTP might be a layer 2 Ethernet or a layer 3 IP protocol, there is no network between these. It's effectively a direct physical connection. So then in this example, we've got the classic London, Amsterdam, Frankfurt, and Paris data centers, all connected via dedicated fibers, dedicated wavelengths between them. And the high performance boundary clock will give you better than 5 nanoseconds of error. So in this particular example, the way this is drawn, we've got one node that has the GPS reference, it has the cesium backup, it has the blue sky in there as well to look at the to assess the quality of the live sky signal. But there's no reason why you couldn't deploy that at every single location here. And if one of these went offline, or even if two of them went offline, they can still maintain over the physical network better than 5 nanoseconds error to whichever node is active and providing the reference. So virtual PRTC, VPRTC, is a new networking technology that's enabled by this high performance boundary clock mode of the time provider 4100. So in terms of solutions for increasing the performance, increasing resilience and security within data centers, we have security and time traceability by using Blue Sky, using the GNSS Firewall. Atomic clocks add resiliency, so we add that into our into the portfolio, into the solution that we deploy in the data centers. And the sync servers and grandmasters the time provider 5100, the S600, S650 support both NTP and PTP to support all the applications that might be in the data center. So, to summarize, requirements for time are increasing. We're seeing that across all market segments to enable new technologies, new features, new solutions and services that some data center operators want to deploy. Time requirements are increasing. Security is obviously paramount. Auditing and testing of these time systems is a must as well. Sometimes that requires specialist equipment. We do offer, Chronos offers time auditing services where we will audit the design, the deployment, and actually go to site and measure these timing systems, particularly for the MiFID II requirements to where they have to be traceable to within a certain era of UTC. But time as a service, this idea of selling time, deploying equipment like I've described in a data center, and then offering secure, resilient, and traceable time as a service can increase security resilience and, importantly, attract more customers into data centers. So not just space, power, and cooling, but the smart data center offering, I think, should be space, power, cooling, and time as well. So that's it. That's the end of the slides. My colleague Frank von der Merlen is available if anybody has any questions, wants to contact him after the webinar is over. So thanks for listening.